Welcome, this is Semantic Web Technologies, Lecture 4, Knowledge Representations. Part 5, Foundations of Logic. So, what we want to do now is we want to represent ontologies with the help of logic. We have seen that this can be done via description logics. And description logics, we also have learned, is somewhere between propositional logics and first-order logic. It means it is a fragment of first-order logic that is restricted in some sense while preserving some of its expressivity and, on the other hand, reducing its complexity. But when we try to understand how we can make calculations on top of that knowledge, we have to take a look at the foundations of logic. So, logic is quite old, you know. The term logic comes from Greek. Logos in Greek means word or study. And for our purpose, logic is the study of how to make formal correct deductions and inferences. And we need formal logic because we want to automate that process and we want machines to make this process instead of us. So we want to construct a calculator machine for logic. And this is a pretty old idea. Even in the Middle Ages, we have seen this in our philosophy part of the lecture. Raimundus Lullus, a man from Spain, he defined logic as the art and the science to distinguish between truth and or lie with the help of reason, to accept truth and to reject lie. And for this, he constructed this tree of knowledge that was based on the Aristotle categorization of the world, on Aristotle's categories. Later on, in the times of Enlightenment, Gottfried Wilhelm Leibniz, famous mathematician, came back with this idea and said, if we are able to express our thoughts with the help of logic or mathematics, then we would be able to calculate the answer of a dispute, and we would not have to struggle or to argue. So, he said in a letter, the only way to rectify our reasonings is to make them as tangible as those of the mathematicians, so that we can find our error at a glance, and when there are disputes among persons, we can simply say, let us calculate, without further ado, to see who is right. So, and this is what we want to achieve. So, first of all, in logic we have syntax. But syntax are only symbols without meaning. It means the syntax defines rules how to construct well-formed and valid sequences of simple symbols, of strings. On top of that, we have the semantic. And the semantic defines the meaning of the syntax. So the semantic defines rules how the meaning of complex sequences of symbols can be derived from simpler ones, from atomic sequences of symbols. Small example here, you have the syntax of a programming language. Here, for example, if I is smaller than 0, then display negative account. So it means this simple sentence or statement in programming language means that print the message negative account if the account balance is negative. So this is the assignment of meaning. But we will see that there are different types of semantic. The first and most natural thing is the so-called intentional semantics, so the meaning intended by the user. And this restricts the set of all possible meanings, of all possible models, to the meaning intended by the human user. So for example, for this little fragment of code you see here, there a factorial is computed. And the computation of the factorial is the intentional semantics. So that's pretty simple. But on the other hand, we also have the so-called formal semantics. And here you see in the formal semantics for this expression given as a programming language, we have here the mathematical definition of what a factorial is. So the formal semantics aims to express the meaning of the symbol sequences in form of a formal language in a way that assertions over the symbol sequences or over the programs can be proven by the application of deduction rules. So this is the formal semantics. And for programming languages, we also have a so-called procedural semantics. And the procedural semantics defines the behavior of the program at execution time. It means the meaning of a language expression is the procedure that takes place internally whenever the expression does occur. So this is the procedural semantics. We will see that for logics, the most important semantics for us is the so-called model theoretic semantics that has been introduced by Alfred Tarski. And the model theoretic semantics performs semantic interpretation of artificial or human or natural languages by identifying meaning with an exact and formally defined interpretation with a model. So therefore, model theoretic semantics. We try to define a model as an informal interpretation of the language. So, for example, for propositional logic, the model theoretic semantics is the assignment of truth values, true or false, to atomic assertions, and the description of logical connectives with the help of truth tables. So, therefore, we make a model for propositional logic. We will come to that later in the part of the lecture. But in general, how does logic work? Quite simple. You have, for any kind of logic, you have a set of statements. And to deduce or infer new knowledge, you need some kind of an entailment relation. So a logic consists of a set of statements and entailment relation. And then, from a set of statements, let's call it phi. It's here big phi, which is a subset of S, which is the set of statements. You can entail, with the help of this entailment relation, another statement, small phi, which is also an element of the set of statements. So big phi entails small phi. Small phi is a logical consequence of the set of statements represented by big phi. Or from the assertions from big phi follows the assertion small phi. On the other hand, vice versa, if for two assertions, phi and psi, both element of the set S of statements, if for them holds that phi is a logical consequence of psi and psi is a logical consequence of phi, and here you have to consider that here at the right side of the entailment relation always there is a set. Therefore, also for a single relation, we consider the set of this single consisting of this single relation, and this entails the other relation. So if both hold, vice versa, then both phi and psi are logically equivalent. So with these two things, the set of statements and this entailment relation, each logic is defined, and this is the way how a logic works. What we need to do, we have to make the entailment relation now explicitly, so we have to define a model for the entailment relation. Okay, first let's take a look at the most simple logic, at the propositional logic. In the propositional logic, or simply PL, you have a small set of logical connectives. It's the negation, conjunction, disjunction, implication, and equivalence. And you have a set of symbols. And of course, these both sets are disjoint. And on the other hand, you have the two truth values, true and false, that have been applied or assigned to your statements. And then you have production rules for propositional formulas. They are also called propositions. And of course, all atomic formulas are propositions, so it means all elements of sigma are propositions. And then, of course, if sigma or if phi is a proposition, then also not phi is a proposition. And if phi and psi are propositions, then also both of them connected with a set of logical connectives. It means and, or, if, then, or equivalent. They are then also propositions. And there are certain priority rules. It means the negation is prior to the conjunction and disjunction, and this is prior to implication and equivalence. How do we model facts with propositional logic? Pretty simple. For example, if you say the moon is made of green cheese, this is a simple fact, and this can be modeled with the symbol G. It rains can be modeled with the symbol R, and the street is getting wet can be modeled with symbol N. And with these three simple assertions, we can make more complex assertions and more complex statements. For example, we can compose assertions like, if it rains, then the street will get wet. So, if R, then N. R implies N. Or, if it rains and the street does not get wet, then the moon is made of green cheese. Something new. So, you say then R and not N implies G. So you see propositional logic is pretty simple. Now let's come to a model theoretic semantics for propositional logic. Therefore, what we have to do is we have to map all atomic propositions to true and false. And this is pretty simple. So for example, we have here two variables or two constants, and they can be both false, one of them can be true, or both can be true. And then we have to consider what happens when we consider the negation of one of them, what happens when we consider the disjunction, the conjunction, the implication, and the equivalence. And this is the according truth table, where true or false is assigned to this proposition according to the assignment of P and Q. So for example, if P is false and Q is false, then the implication P and Q must be also false. So in this way, you decide which interpretation is given, so which truth value is assigned to a complex formula in propositional logic. And you can prove this via truth tables. So it's pretty simple. For the model theoretic semantics of propositional logic, of course, you need the entailment relation, and you say that, for example, F with the interpretation I, F is true. It means that the interpretation I is a model of formula F, and then you write here that I entails the formula F. So you have here the right interpretation. And this entails then the formula F, means then the formula F is true. And then we call this interpretation I a model of F. And the rules for semantics are pretty simple. So I is a model of not F only then if I is not a model of phi. And I is a model of phi and psi only then if I is a model of phi and I is also as well a model of psi. And so on and so on. And these are the rules then for the semantics. And then we define some basic concepts. For example, a tautology. This is an assertion or a proposition that is always true. Then we define the term satisfiable. It means there is a satisfying assignment of variables that a statement, a complex statement, is true. On the other hand, a statement can also be refutable. It means that there is an assignment that is not true for that complex statement. Or it's unsatisfiable. That does not exist any assignment that a given complex statement is satisfiable. So then it's a contradiction. Okay, pretty simple for propositional logic. A little bit more complicated for first-order logic. In first-order logic, in addition to the logical connectives, we have these quantifiers. Let's remember, first-order logic has the possibility to make assertions and to make statements about sets of things without naming these things, or without naming the individual things. For this, you have the quantifiers, the existential quantification and the universal quantification. Then, in first-order logic, you have variables. Here, mostly written in capital letters. Then you have constants, and you have functions. And for those functions also, you have an arity. So it means the number of arguments is given. And you have relations and predicates. And then you can form complex statements. For example, like here, you say, for all variable x, there exists a variable y where the predicate p of x and not q of x of f of x and y implies r of x. So this is pretty complicated to read, but it's understandable by a machine and can be interpreted correctly by a machine. And it's a statement, a complex statement, a formula in first-order logic. In first-order logic, you distinguish between so-called terms. Terms are made from variables, constants, and functions. So here have you a selection of different kind of terms. More complex then are so-called atoms that are relations with terms as arguments. So here, for example, greater than, and then you have x location of pixel. So this is an atom. And then if you also additionally to the atoms apply operators and quantifiers, then you have a formula. So for example, for all pixels, it holds that here, for example, if the location of a pixel is greater than 128, then this must be a red pixel. So pretty simple, only the terms are a little bit more complex. Overall, if you make statements in a first-order logic, use brackets whenever you are in doubt about the priority. And all variables, of course, should be quantified. So if a variable is not quantified, most times we assume that all of its assignments should be meant by that statement. So if there is no quantifier, it will be interpreted as a universal quantifier. So how do I model facts with first-order logic? Pretty simple. For example, here you have all kids love ice cream. In first-order logic, you say, for all variables x, it holds, if x is a child, then x loves ice cream. Pretty simple. You will have in the exercises, again, translations that you have to do between natural language and first-order logic to train these capabilities and to train this to translate first-order logic into natural language and vice versa. Let's take a look at another sentence. For example, the father of a person is a male parent. In first-order logic, this fact is simply expressed for all x and all y. It holds that if x is the father of y, then, and only then, x is male, and x is parent of y. Another thing, there are one or more interesting lectures, so there exist interesting lectures, which I hope. Then you say this fact in first-order logic, there exists the variable x, where x is a lecture and x is also interesting. So you see here, you can define facts with first-order logic. And of course, you have here much more expressivity compared to propositional logics, where you could only make facts and statements about single objects and not about sets of objects, for example, also about classes and objects that are not directly named. Okay, another one. The relation is neighbor is symmetric. You also can state this in first-order logic. So for all x and all y, if x is a neighbor of y, then y is also a neighbor of x. Pretty simple. So if we want to take now a look on the model theoretic semantics of first-order logic, then first of all, we have to define a domain that we consider. Then we have to map all constant symbols to elements of D. And then we have to map all function symbols to functions in this domain and all relation symbols to relations over this domain. Then automatically assertions will become elements of D of the domain, and relation symbols with arguments will become true or false in the end. And logical connectives and quantifiers are treated likewise. Let's take a small example. So here we have a more complex expression given in first-order logics. So what does it mean? I try to translate it for you. It means, let's take a look at this. All penguins are black and white. And some old TV shows also are black and white. Therefore, so this implies that some penguins must be old TV shows. So okay, this doesn't make really sense, we know that. But on the other hand, we have to find a mechanism to prove this. And we can prove this if we find an assignment of the variables given here that doesn't fulfill this formula. So when the formula in the end is refutable, it means it's not a tautology. There is an assignment that this formula is wrong. Okay, so let's consider a domain. So for example, a set M that contains elements A and B. We have no constant symbols here. We only have variables. And now we show that the formula given here is refutable. So it means it's not a tautology. So, for example, we start here and we take here a symbol or an element of our set A. It's A. And say, first we interpret here penguin, or the interpretation of the penguin, where we take A as one of the placeholders for this variable X. And we say, we take black and white, also interpretation with the symbol A, and we take all TV shows B, and black and white B. This should be true. So penguin, A should be a penguin, A should be black and white, B should be a TV show, and B should also be black and white. So this is true. Then, if we assign A is not a TV show, and B is not a penguin, then the entire formula, if we substitute these interpretations, it means these elements of our set M, A and B, into the positions of the variables with the assignment that this here is true and this here is wrong, then the formula will also compute wrong. So it means that here, this interpretation will not entail the formula F and is not a model for F. And therefore, we have shown that this statement is not always true. It's not a tautology. So in daily life, for us, it's pretty obvious. Of course, penguins are black and white, some TV shows are black and white, but this is not the reason that some penguins might be also an old TV show. So this is quite obvious. But if you find an interpretation, it means here an assignment that holds or that is consistent and that computes for this formula false, then you have formally proven in an automated way that this assertion or this statement really is wrong. And this is a nice thing. Okay, let's take a look at logical entailment in first-order logic. We have a new concept. It's called a theory, and a theory is a set of formulas. And therefore, a theory is pretty much the same as a knowledge base. So then an interpretation I is a model of T, only then if for all formulas G in T, I is a model. And the formula F is a consequence of T only then if all models of T are also models of F. So then we can write that T entails F, or F is a logical consequence of the knowledge base T. On the other hand, we know this already, two formulas F and G, also in first-order logic, are logically equivalent if and only if G is a consequence of F and F is a consequence of G. And then we write F is equivalent to G. So what we have learned now is we have taken a deeper look into propositional logic and first-order logic. And we don't do this in much more detail because this already should have been part of your lectures as a computer scientist. This is basic stuff. What we will do next is we will take a look at so-called canonical forms and on the calculus that is used to automatically deduce satisfiability or contradictions from a given knowledge base and for given formulas in first-order logic and then also for description logics, because this is what we were all about in the first place. So we wanted to construct an automaton or a machine that is able to use logic for reasoning. So we will see this in the next part of this lecture, and we will continue with the canonical forms.